All right, so let's look at this problem. So, that glare is too much. Is that better? Yeah. So we've got a cantilever beam, so you can see there's a fixed connection at A, and we've got all these different forces applied, and there's even a moment applied out here on the end. And we want to find the internal shear force and bending moment in the cantilever at a section through C. Okay? So what I like to do is first go to that point C and kind of draw a line. There's my section. And then I have to ask myself, do I want to work the left side or I want to work the right side?
Right side.
Yeah.
Right side.
Yeah, if you did choose the left side, that's okay, it will work, but you have a little more effort to put out because you've got to find the shear force and the bending moment here at A. So in this case, we're going to look at the left-hand side. So I'm going to draw a quick diagram of the left-hand side. So there's my element. And I'm going to draw on... I'm going to do everything in kip. So this will be half a kip. And the end will be half a kip. And then there's a moment applied at the end of 2 kip feet. And this dimensions are 10 feet and 10 feet. Now here's the tricky part you got to think about is this 500-pound force on this part or on the part on the left?
It's on this part.
It's hard to know. So what I'm going to do is I'm going to include it and say that I'm not cutting this at C. I'm cutting this just to the left of C. So that means I'm actually cutting it on the left-hand side of C, and I'm getting as close to the force as I can, but I didn't go past it. So it's just to the left of C.
Question.
Yeah.
Now, if you solve the other side based on this information already put down, would you include it on the left side, or would you include it?
Well, we're going to redo the problem in a second, and we're going to cut it just to the right of C. And when I cut it just to the right, the half kip is not included. So on my left side, I'm going to assume the positive axial force. I'm going to assume positive shear, and I'm going to assume positive bending moment. I guess I should subscript those C, and I'll put a little minus sign indicating that it's just to the left, kind of the minus side of C. And once I make that decision, I can solve for those values. So the first thing I'll do, as we mentioned before, is I will sum moments about the cut that I just made. Make sure it's in equilibrium, and I'll assume right-hand rule for my sign convention. So starting with the unknown moment, what kind of moment is that with this sign convention? It is negative. So I will write minus MC just to the left. Does this first half kip force create any moment about the cut? No, because remember, I've got as close to it as I can. Even if there was a moment arm, it'd be really, really, really small, so it'd really create no moment. So it will not. But I will get moment by the other 2 half kip forces. And what kind of moment will they be, positive or negative?
Negative.
Negative. So I'll put that out front. So there's my half kip force. And the moment arm to the first one is 10 feet. And the moment arm to the second is 20 feet. And then all the way out here on the end, what do I have? Another moment. Is that positive or negative with my sign convention?
Negative.
Negative. And that's just 2 kip feet. So I can solve for the moment at C. And when I do that, what do I get? I get minus 17 kip feet. So it says the moment at C is negative. Does that make sense? Well, let's go back and look at this beam. How do you think this beam is going to bend? Is it going to bend up? No, it's probably going to bend. This is exaggerated, but it's probably going to bend like that. And if you look at that, that's kind of half a frown. So I would expect the moment in this entire structure to be negative. And I got a negative value, so I feel pretty good about that. It's kind of weird to say I feel good about a negative, but I do. What's next? Let's find the shear force. So we do that, we'll just sum forces in the y direction. Again, make sure it's in equilibrium. So again, I'm assuming up is positive, so I go over here and look at my shear force, and it is up. Then I've got 1, 2, 3 half kip forces acting down. So I'll say minus 1/2, minus 1/2. I could have easily added them together, but I'll just do it this way. And that's it, right? Because I don't add moment into a sum of forces, and I've already accounted for it here. So I should be able to solve for the shear. And what is it? Looks like it's positive 1.5. I guess technically I'll come over here and just say, yes, I will check that when I sum forces in the x direction, all I have is, in my case, I have axial force going to the left, but it doesn't matter, it's 0. Okay? So now I'm going to not cut it just to the left, I'm going to cut it just to the right.
Now, we already have our answer to this question.
Do we?
Yes.
We have maybe the answer to the question. We have to think about it. This is the reason I like to work this problem to get started. I want you to see that sometimes you maybe can't get the answer that you want or that you think. So I'm cutting it at the same place, except it's just to the right. So in that case, I still have my half kip force at 10 feet and my half kip force out here at the 20-foot mark. And of course, I still have my moment. But this one is not there because since I cut it on the right-hand side, that 500-pound force is on the other body, the left side body. And I will assume, again, positive axial force at C, and I'll put a plus sign there because now I'm just to the right of C. Don't worry so much about this notation. I just want to do that to show you the difference. You'll notice my sign conventions are the same. And we can start. So just like we did before, we're going to start with summing moments at the cut. So I'll do that. Again, I'll assume right-hand rule for my sign convention, and we will sum moments at the cut. Make sure it's in equilibrium. So looking at this free body, again, my internal moment with this sign convention ends up being negative. I have to deal with the moment caused by these two forces. They're both a half, and they also create negative. So the force is 1/2 kip. The first one has a moment arm of 10 feet. The second one has a moment arm of 20. And then out here on the end, what happens? I've got the negative applied moment, which is 2 kip feet. If you look at these two equations, they are the same. So it looks like the moment at C, whether you cut it just to the left or just to the right, doesn't seem to affect the moment. What does it affect? Well, let's find out. If I sum forces now in the y direction, what do I get? Well, I look at my free body diagram. I have a shear force that's up, so I'm calling that positive. I have 2 1/2 tip forces down, not 3, just have 2. And I think that's it. So it looks like the shear at C just to the right is equal to 1. So it does make a difference in the shear value depending on where you cut it. In fact, if we look at that, what's the change in shear from going from the left side going to the right side? It's negative 1/2. And look at the force that I went under from left to right. It's also down, which means it's negative 1/2. So the change in shear is equal to the applied point load. So every time you see a point load and you go from left to right, we always go from left to right, that's positive sign convention, right? Positive X. You'll see the shear instantaneously drop exactly the amount of the load. So if I actually made a little plot of the shear force, and I'm only interested in point C. As I come from the left side, what's the value? It's 1.5, right? And then I go under C and I go to the right, it's only 1. So you don't have to worry about what else is going on. But you do see that I've got this change in shear is going to be equal to the load. So that just seems anecdotal now. It worked out in this problem. But we'll find out later that we'll prove this mathematically. So this is going to be something that we can use later on to help us see how shear force varies across the structure. Every time we encounter a concentrated load, we know the equation is going to change instantaneously. So if this were the graph of the curve, you would see it step down. So then it's kind of tricky. What is the shear at C? You don't really know. You know to the left, it's 1.5, and you know to the right, it's 1. Now, which of those is going to control your design? The largest magnitude, which would be the 1.5, would be more important. All right? The moment, on the other hand, has the same value. So the moment does not have an instantaneous jump or step as you move through. There are times where it does jump, and that's where you have applied moments. Okay, any questions about that?